hello. Hello, hello. go.
Yes. Post,
Where does, like, do I have to stand anywhere specifically? Part. Sorry. Actually, I guess. Oh, okay.
I'm gonna keep you guys.
Yeah, just I'm definitely I can if I have like once I get to a certain point, it's all right just to end it. So just let me know how I'm doing time wise.
That's the 1 minute.
It's on. Well, yeah, I gave this and much more before. I mean, this is like, I had to scrape, oh yeah, I had to scrape it down so much. I think the original presentation was like 28 slides. It's like 9. Yeah, that's not gonna happen. I mean, basically all the MATLAB stuff, I just axed for the most part, just because now. Oh, well, yeah, I mean, I only included one of them because you really only need to see one of the tables just to see. And then, but even just getting through there is like 7 minutes. So it's pretty difficult to like introduce a topic and then give the data and conclusions in only 10 minutes. But well, I'll do my best.
So we stay on schedule. First, I apologize on behalf of the speaker. They had a medical emergency, so he couldn't show up, and I do thank the students who stepped up to the plate and agreed to present and fill this seminar slot. So we're going to have 5 speakers today, and we're going to introduce them one by one. I warned the speakers I'm going to keep them on schedule, so we'll get us out of here at 15 minutes after the hour. So for the speakers among you, you're going to have 9 minutes of speaking, 1 minute of questions and answers. So 6 minutes in, I'm going to do this, meaning you have 3 minutes. 1 minute after that, 2 minutes after that, I'm going to do this. And if you don't stop in 1 minute, something bad is going to happen. That is unspecified. So the first speaker today is Nate Hart. Nate got his bachelor's from New Mexico. Then he came and joined my group. He's working on area analysis, spatial discretization area analysis for the discrete ordinance methods. But this summer he went and worked. He's been actually going to Los Alamos for 3 years now for the summers. And this year he did this work that's not related really to his PhD thesis on alpha eigenvalues in partisan. So
Yep. Thanks for the introduction. So yeah, this summer project, finding high order eigenpairs of the alpha eigenvalue problem in partisan. Before I start, I want to thank my mentors, John Dahl, Aaron Davis, and Randy Baker. They really kept me busy over the summer. So here's a quick overview of the presentation. This is kind of cut down from a much larger presentation, so hopefully with the time limit I could still give you guys a decent understanding of what I actually did this summer. So first I'm going to introduce the alpha eigenvalue problem in the discrete ordinance method. So shown here is the steady state neutron transport alpha eigenvalue equation. For those of you who do anything with neutron transport, you probably think that this looks sort of familiar except for this term right here. So the way we actually get this alpha eigenvalue equation is by assuming that the time-dependent angular flux is separable in time, as shown here, and moreover that the time dependency can be expressed with an exponential, where alpha then describes your time rate of change. So if alpha is greater than 0, that means that your neutron population is increasing or you're supercritical. And if alpha is less than 0, that means your neutron population is decreasing, you're subcritical. And so basically, this is different than the time-dependent transported equation in the sense that this term replaces the time derivative in the time-dependent transport equation, and thus it becomes what we call a time absorption term, and now it's a steady state equation. We solve this just as you would any other eigenvalue problem, but now we're solving for alpha, which is the time, basically describes the time rate of change of the neutron population. Typically, interested in solving the alpha eigenvalue equation, only solve for the dominant alpha eigenvalue. And this is because you're really interested in how the neutron population behaves with time. As time gets longer, what neutrons are going to dominate your system. As you can see by looking at the exponential, that means that basically you're looking at the largest real alpha eigenvalue. So if you have a supercritical system where alpha is greater than 0, you're very quickly, your fastest are going to predominate your system, and vice versa for a subcritical system. Very quickly, the neutrons that are decaying away the slowest, they're going to dominate your system. However, what you kind of lose some information by doing that, and that's the fact that alpha is not really just a single value. Alpha is an eigenvalue that exists as a spectrum, and in fact, alpha it exists as a spectrum on the complex plane. So most people aren't typically interested in these higher order alpha eigenvalues, but there are certain niche groups, especially at Los Alamos, that are interested in those higher order alpha eigenvalues. So essentially, my summer project was to use, well, before I go to that, I'll introduce Partisan. I worked for the Partisan group at Los Alamos, and some of you might have used Partisan or at the very least are familiar with it. It's available on RSIC. But Partisan is a Los Alamos discrete ordinance transport solver. And basically what we can do in Partisan currently is solve for the dominant alpha eigenvalue, because like I said, for most people this is all you want. But my summer project was basically putting the capabilities into Partisan to solve for these higher order alpha eigenvalues. And that's harder than it sounds, because with the methods that are already in Partisan, there's no way that you can do that. So we basically had to put in a new, completely different method for solving the transport equation than we otherwise would, so that we could get these higher order alpha eigenvalues. So the question then was which method? Well, we settled on the generalized Davidson linear solver because for two reasons really. One of them was that it has been successfully demonstrated in the past for solving higher order K-effective eigenvalues. And actually, the people who developed capsaicin, which is another discrete ordinance transport code at Los Alamos, they used the generalized Davidson method as well to get alpha eigenvalues. So we knew that it had some very desirable properties. The capsaicin team actually used the Trilanos solver library, which is developed by Sandia. So we were really interested in using that solver library, but the problem is that Trilanos is a C++ solver library, and Partisan is written in Fortran. But luckily, the planets kind of aligned, I guess, and Oak Ridge is actually currently developing an interface, a Fortran interface to Trilanos that they call ForTrilanos, and they put the call out to the national labs saying, hey, we're interested in people using our interface. If there's anybody out there that wants to use it, we would fund you. So basically, that's kind of where I come in, is now I'm using ForTrilanos in Partisan to use the generalized Davidson method to solve these higher order alpha eigenvalues. So how did my summer go? Well, it was generally a success. I was able to put the generalized Davidson solver into Partisan. I was able to put the generalized Davidson solver into Partisan, get some higher order alpha eigenvalues, but I'm going to say right now that it's still a work in progress. The fact is that Fortrillinos is kind of in the alpha phase of development, so it's not necessarily user ready right now, but we're still able to get the results, and I did a quick study that I'll show you in a second to show that they're good results. The first thing I did was I checked the dominant eigenvalue that I obtained with this method to make sure it matched up with what Partisan had been getting before, and I found that it was. It's not terribly exciting, so I didn't show it, but we really needed a reference for the higher order alpha eigenvalues. And well, I already mentioned that capsaicin had basically already done this, so we decided to look at their results, and it was especially advantageous because they used the same solver we did, but then we kind of wanted to know, well, are those results good? So we looked at this Kornreich and Parsons semi-analytic benchmark where they were able to solve for some of the higher order alpha eigenvalues. And before I show you the results, alpha eigenvalue is not a unitless quantity like K effective. It does have units, and they're in inverse shakes, which a shake is 10 to the negative 8 seconds for somebody who doesn't know. So I basically ran a bunch of these benchmark problems. I'm only going to show you one because the story is pretty much the same for all of them. We're looking here at this Kornreich and Parsons benchmark number 2, where the parameters are shown here. The discretization parameters are right here. And first thing I want to draw your attention to is the fact that Partisan and capsaicin basically agree perfectly. This is a great sanity check because we're doing the same discretization parameters as capsaicin. We're using the same solver as capsaicin. We should be getting the exact same results, and we do. The next question is whether or not we agree with the semi-analytic benchmark, which is kind of taken to be the correct answer. And basically we do. You can see there's some deviation, like in the 3rd decimal point, in the 2nd decimal point here. But really, this is a relatively unrefined discretization. If we further refine the discretization, we would see better agreement. But you do see the trend where generally when you look at higher order alpha eigenvalues, you require further refinement. And then because I'm kind of running low on time, this is just kind of what I just did. This is not Partisan results. This is just a MATLAB code I had been playing with to get the full discrete spectrum of the alpha eigenvalue. But this kind of puts a complete picture to what I had been saying about the alpha eigenvalue. So the dominant alpha eigenvalue is going to be the most real one here, but you can see that it really exists as a spectrum on the complex plane. And specifically, the higher order alpha eigenvalues exist as complex conjugates of each other. There's a lot more that I could show, but we're going to move on. So just some quick conclusions and potential future work. Basically, even though it probably won't be in any release anytime soon, Partisan can now accurately calculate higher order alpha eigenvalues using the Fortrillinos interface and solver with the generalized Davidson method. There are some other questions that could be answered that are listed here, but I think my time is basically up, so thanks for coming and listening. Yeah, so they did, it was, I don't know exactly how they did it, but they used a lot of Green's functions, and they were able to, I don't know if they were doing really any fitting. It was all Green's functions, I think, but yeah. But I will say that, I didn't mention it when I was on the slide, but their semi-analytic benchmark is not able to get the complex alpha eigenvalues, so.
Thank you very much, Nate. Do you know how to get your?
It's on the desktop, I think.
Okay. So the next speaker is Dylan Holden. Dylan got his bachelor's here, and then he joined my group. His work is related to acceleration of interactive methods for solving discrete organ solutions and massive material architectures. And this summer he went and worked at PNNL. And the work that he's going to describe is, or present is based on that work that he did there. That's also represented.
Thank you, Dr. Azmi. So this is going to be on a joint transport gamma modeling of the collimator and passive gamma emission tomography. So passive gamma emission tomography, or PGET, as I'm going to refer to it from now on, I'm going to go to a very, very brief overview of it. Effectively, it's something that you're going to use to get a pinwise gamma emission distribution from a spent nuclear fuel assembly. How it works is effectively you're going to have just a giant block of tungsten that has a bunch of really, really thin slits cut in it with a detector at the base of each one of those slits. The idea, if you think you're that detector and you look through it, you're not going to see much of the assembly. You're just going to see a very small portion of it. It allows you to get spatial resolution and deduce where those gammas came from whenever you get detection, so they can use that alongside with their imaging methods to construct the gamma emission from the detector responses you get. Now, if you think of that from a deterministic transport standpoint, it's incredibly tough to model because of the ray effects. So if you have any kind of discretization with the angular domain, then what you're saying is you're only defining your transport solution along certain directions. And if you think about two very nearly adjacent directions going into that slit, because the slit's so narrow and so non-reactive, what's going to happen to gammas entering at these two directions is going to be very different. So you're going to have a very, very refined angular mesh in order to get any kind of accurate solution to this. And so what we were looking at is effectively how to use adjoint transport in order to both study the collimator and to create what we're going to call a collimator response function, or a CRF, which maps whatever is coming into the collimator inlet to the detector fluxes with just a simple dot product, as opposed to having to actually run these really computationally intensive runs over it. And so what we're going to look at is effectively adjoint transport. You can interpret it as two different things. You can interpret it as a response function or an importance function, and the two are going to be kind of interlinked. So the response function is the ultimate goal. You want something that just mathematically maps what's coming into the collimator just instantly to what's going into the detector. And as an importance function, what you do is you kind of recursively simplify that response function by looking at what parts of the problem are important, what angles and what directions, angles and locations in phase space are actually going to contribute to the detector response, so you can ignore what isn't. So first thing to do is to converge that solution. I mean converge not iteratively, but on a spatial, angular, and all the other meshes you need. So everything converges quickly except for the LCF quadrature. What LCF stands for last collided flux, and it's a manner in which you can get a more accurate solution at whatever point you need. So effectively what it does is you have your transport solution everywhere. You say, I want a more accurate solution at this one point. It's going to run a ray trace from that point, and it's going to use the scalar flux and all the cells that ray trace intersects to deduce the solution at that point. And so since this is just a ray trace, it's a very simple calculation, it's not an iterative sweep, you can do this with a much, much higher angular quadrature order in a feasible amount of time than you could, say, the entire problem. And so we're trying to converge that LCF quadrature, and we see what we have here is an adjoint run where you put a source at the detector location, and then we're looking at the adjoint flux on a line across the collimator inlet perpendicular to the slits. And so we see as we start getting away from where the detector is right here in the middle, as we get to the sides, it converges very quickly at reasonable quadrature orders. When you're in the middle, we're at S1000, and it's still, not only is it not converged, but we're not even in the asymptotic region yet. It's still oscillating pretty wildly. So if we just look at that point, just 0.15 centimeters on either side of the center slit, and we can see that it takes us up to S1800 to finally converge that. So that's the manner of the ray effect that we have in this, that it's that detrimental to the solution, that you have to go that high, because that's about 3 million angles that you have to have in order to accurately model this then. So with that converged solution, what we do is we don't do that for the whole thing, because that would be just insanely long to run. We just do that for the center part, and then as you go further and further out, you have an increasingly diminished quadrature order as you get to further and further away slits from the center, because you don't need those for convergence. And then this is a little trick we did with the software package we have. If you do a point source, that's a delta function mathematically. Computationally, you can't really manifest a delta function. What they do is called a first scatter distributed source. And what the ultimate effect of that is that the LCF does not include the uncollided flux in its solution. And so we use that as a little trick to try to separate the collided from the uncollided, because one of the things we were wanting to look at is, can gammas scatter within the collimator and then stream to the detector and be picked up? Because that was one thing that was being neglected in RadSat, which was the formal way of modeling this. And so this was it was not the actual not the actual setup, but it was something that gave us a high-end estimate that as much as potentially 25% of that could be collided within the collimator. So that was something that cannot be ruled out as a potential cause of the discrepancy that RadSat and MCMP were seeing with one another. But that is a high-end estimate because we're just looking at the adjoint at that point. The adjoint, it's only half the picture. You have to look at the forward solution as well, because while an angle at a certain direction can be important to the solution, if there's nothing there, then it doesn't matter at that point. So what we're graphing is this equation right here. That's just the adjoint multiplied by the forward solution, which we're effectively treating as an area-wide flux, and then integrating over angle. And what we can think of this is this is a detector response as a function of where that gamma radiation initially impinged on the collimator inlet. And what we're able to get from that, thank you, in addition to being able to eventually ascertain the detector response from that, is we get these numbers right down here where we can look at the collimator inlet and say, how much of this do we need to model? And when we look at it, we can see, well, not that much. 2.4 centimeters on either side of the center slit will actually get you 99% of the detector response, meaning that you can drastically simplify that collimator response function at that point because you could just get rid of everything else that's on there and not consider it. Another thing it helps us do is to look at interdetector scattering. This is something that they thought might happen. You could have a gamma that goes down, hits a detector, and then scatters to another one. Well, we were able to prove with that last graph I showed you that that can't happen. Well, it can happen, but it's incredibly unlikely, because if we look at this diagram over here, 2 detectors and then a gamma ray coming in, scattering off one and going to the other, gammas lose quite a bit of energy when they scatter, especially at sharp angles. So if we consider the highest energy gamma coming in this problem, which is 1333 keV, and then the bottom of the detection window of the detector, which is 700 keV, you can't have an angle of more than 42 degrees and still get a detectable scattered gamma. And if we then extrapolate all the way back to the collimator inlet and look at that map we just had, and we integrate it, we find that it is an astronomically low amount of those gammas that reach that detector that are then eligible to scatter to adjacent detectors and still be above 700 keV. And so the final thing we do is then we effectively just take what we had at the other, that's weighted summation from a few slides ago, and we just integrate it over the area of the collimator and the detector volume, and what you get is the detector response then. And so what we're looking at is on that collimator there are tons of detectors, so 0 is the center detector, and then you're just going to the left and right of it, and we're looking at the detector responses, and what we can is that it fairly closely resembles RadSat, which unfortunately was not what we were hoping to have. We were hoping it would agree with MCMP because that would be more logical then we would have a reason for why those two disagreed and why we got the agreement now. But what this does for us instead is now we've realized that you can take a very, very computationally intensive portion of a project, or excuse me, a problem, and you can just kind of separate it and model it with adjoint transport because this is a one-time run. Yes, it was incredibly costly, but then you have a response function that then maps whatever is coming in on that problem boundary to the quantity of interest, and you can also recursively then simplify that because of looking at the adjoint as a importance function. You can find out what parts of that you can safely neglect back to your solution accuracy. So, with that, I'll take any questions. Thank you very much. Yes, sir. Yes.
So you wanted to say that I can get 100% if I increase the length?
You could get 100% if you went all the way to the end of the collimator. Yes. But the end of the collimator is also what the collimator we were looking at is already a small portion of it. It goes very, very large and tons of slits. So it would greatly increase the cost of it. Anybody else?
One more quick question. We're good?
Yeah, thank you.
Thank you, Dylan. Is Pascal here?
Yep.
I apologize if I mispronounced your last name.
No, it's perfect. That's great.
Is Pascal Boxley?
Yes.
He got his master's degree in 2012 from the University of Provence, USA. He spent a year and a half in an internship in my intervention lab, and he works here with Dr. McEnroe in the area of research and sensitivity and uncertainty, high temperature gas cooled reactors.
Thank you, Dr. Azmi. Good afternoon, everyone. So my presentation today is about an energy group search engine based on surrogate models. I did this work at the Idaho National Lab under the supervision of Dr. Kostadin Ivanov and Dr. Andrea Alfonsi back at INL. So unfortunately, I have 9 minutes, not 10, so I'm going to skip over the various INL activity and go straight to the point. So I was in the Advanced Reactor Design and Optimization division over there. And my mission was basically implementing new uncertainty and sensitivity methodologies in coupled code analysis. So to be more pragmatic, my work was to couple a deterministic code called physics, which was developed at the Idaho National Lab, and statistical analysis software, which is called Raven, also developed at the lab over there. And so just make them work together, okay? The second task of the work, the second subtask of the work was developing physics so that it is compatible, suitable to uncertainty and sensitivity studies. And the third one was demonstrating that those two softwares are working great together and they actually function. So basically, the first two tasks of the work was, well, mainly programming in Python. So this is, let's say, the skeleton of the work, and I'm not going to talk much about that today. I'm more going to focus on the nuclear design application, so the third application, which is more nuclear engineering based, right? So one of the applications of this coupled Raven and physics sequence capability would be an energy group search engine. So let's give it a little bit of background. So if you look at the neutron energy range, it basically goes from several MeVs to 10 to the negative 4 eV. So the energy range is huge. So to perform core calculation, well, you don't even think about using continuous energy. You need to discretize it. The problem is, it's not that easy to do the discretization because you cannot, for example, define even groups. For example, if you want to go from 0 to 10 MeV, you cannot say, okay, I'm going to do my discretization from 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10. It's more complex than that. It depends on, well, pretty much all the neutronics parameters, so mostly the resonances, but also temperature, burn up, the fuel, the moderator. So if you look at the whole picture, generally the nuclear codes offer you they have predefined fine group structures. In the code I was using, it had a 252 groups predefined structure. Unfortunately, so this is already on your at your fingertips, okay? But unfortunately, when you want to run transient calculations, so coupled thermal hydraulics and neutronics, you need to condense even more. So the condensation, so if you look at this plot over there, that simply gives you the number of combinations you have from 252 peaks down to 9. So for example, if you do 9 groups, well, you would have 1 trillion combinations. So that's just a way to say that there is no way you're going to do a brute force approach and say, okay, I'm going to try every possible solutions and pick the best one. You need to be smarter than that. Usually, the techniques are iterative, but one solution could be offered by Raven. So Raven, again, is a statistical analysis tool. So it can overcome the problem of infinite or almost infinite input spaces by developing so-called surrogate models. So the way the surrogate models work, so you have a 5-step approach. So first, you define a constraint. So let's say a passing criteria. So something that would define a good group structure. Second, so for example, let's say 5% of the reference flux, group flux. That's just an example. Second, Raven is going to train. So he's going to randomly generate inputs and try them, and just keep it in the database. And then Raven is going to do tests and training. So based on the data it already acquired, he's going to generate another random input, a set of inputs, and try to guess, okay, is it going to be successful? Is it going to be a good energy structure, or is it going to be a bad one? When Raven has a sufficient amount of successful guesses, it can build a surrogate model. So what is a surrogate model? This is basically a mathematical model that can give you fast solutions of your problem. So let me take an example, a more practical example. Let's say you want to do cake making, okay? So you want to bake a cake, but you have no idea how to do it. So you have on your hands, this is your input space. You have chocolate, you have an oven, salt. You have also booby traps such as vinegar. So stuff you want to use, stuff you don't want to use. The stuff you don't have, of course, you don't have Google. You don't have everything related to Google, including, well, the great search engine DuckDuck. Yeah. So you don't have a recipe handbook or any luck, okay? So step one, as I was defining in the previous slide, you need a passing criteria. So let's say it's going to be your little brother's tasting abilities. So first Raven is going to train. So randomly just generate a recipe and let's say, for example, chocolate, flour, and put it in the oven, and then you give it to little brother. The little brother is happy, right? It's smiling. So let's say it's a passing one. Then you're going to try 10 ounces of vinegar, some eggs, and you put it 5 minutes in the microwave. And you give it to your brother, he's going to puke, okay? So that would be a failure. Then once you've done enough training, you can start Raven can start the training and testing. So from this point on, Raven is going to say, okay, now based on, for example, this one, I'm going to try 2 ounces of vinegar and 2 cups of chocolate, put it an hour in the microwave, and give it to my brother. And I guess it's not going to work. He's going to be sick. So once and it's probably going to be right. So once he's guessed sufficiently enough, a good amount of times, the good result, whether or not it's passing or failing, it doesn't matter. It's just a matter of being able to guess what is going to be the outcome. Well, he can build the surrogate model. So from this point on, Raven would be able to generate a set of recipes that are good enough. So it's the same application for core design. So you just design a core. You have your fine group structure. This is your reference. Raven generates random structures. You collapse. You feed it to physics, and you compare to reference. The advantage of such approach is, first, this is automatic. Second, this is problem dependent. And third, the fine and broad group solutions are from the same code, physics. So you don't have any mathematical discrepancies when you compare reference to the broad groups. The disadvantages is above 20 groups, it requires a lot of memory. So you need HPC capabilities, and also the user needs some experience to define loose enough passing criteria. So you have here an example. So from a paper, I designed a 2D core, and you have in blue the reflux, in red what was in the literature, and here what the surrogate model can do on a 6-group structure based on 500 samples and 20 hours of simulation. So you can do actually pretty good stuff from there. So in conclusion, so this is an automatic search engine approach. The methodology is working for LWRs, HDR, any type of reactors, and it's proven to be working for an HTTR in 2D for 6 groups and a VHTRC in 8 groups, which is kind of nice. Thank you. Yes. Yeah.
The first question is that, do you really need to have the entire range all the way down to 0.1 milli-eV?
Well, I think one of the nice thing about this application is you don't make any assumptions. So you have your whole space, and you don't even make an assumption on the energy cutoff, for example. So in LWRs, usually the reactor physicists are taking 0.62. Some for HGRs they take 3 eV. So in that case, you don't use any kind of assumptions on that matter, which is nice. But if you want, you can. So if you want to add constraints on your spectrum, on your range, you're right. So you would reduce drastically the input space, and it would be easier to survey it. It just depends on how what you want. So what do you want? Do you want something optimized? Do you want a lot of solutions to try a lot of them? Do you want the perfect solution? It's pretty flexible that way. So if you want, let's say, it also depends if you trust yourself as an expert. So if you really don't trust your expert's judgment, well, you don't implement any constraints, and you go for it.
The second question is just a fun question, because you mentioned in the recipe, you know, 2 cups of...
No, I am the little brother.
Oh, you are? You mentioned the 2 cups of chocolate, but you never told us if it has to be dark chocolate or milk.
Actually, at the beginning, I put 90 and 50% chocolate. Is it good enough or what?
Thank you, Pascal. So the next speaker is Yu Zhang. So this is Mr. Zhang works with both Dr. Mao and Dr. Ivanov. He spent an internship in art and national level research. His uncertainty analysis both for light water reactors and sodium-cooled fast reactors.
Yes. Thank you, Dr. Asmi, for the introduction. And I did the multi-objective core optimization in the Argonne. So my project mostly focused on the capability demonstration. And the goal is to demonstrate the NIMS workbench is coupled with Dakota is capable for the sodium core fast reactor design optimization. And I will go quickly through the introduction. So before the optimization, we need to have reasonable core enough to start with. So we selected the so-called ABTR. So the ABTR is the so-called Advanced Burner Test Reactor. It's mainly designed in Argonne National Lab, and it's a pool-type sodium fast reactor. And we studied the metallic field, which is uranium, transuranium, and zirconium. So you can see on the right-hand side, this is the core configuration. You can see it's the inner core region, outer core region, and also the test, the reflector and shell region. So this is basically the core configurations. And we also have it also has the safety control system and test locations because it's a test reactor. And so just a little bit about the ABTR is you can see there are 3 thermohydraulic loops, and it's a pool type reactor. So the reactor core is located in the sodium pool. And before the optimization, we want to have a reasonable core to start it with. So we model the core using the NIMS workbench. And here showing here is the calculation results from the model we have, and also the reference calculation result from the pre-conceptual report. So we have several differences, such as we have newer version of code and newer version of nuclear data. So we don't expect the reference result to be exactly with the calculation result from the model. We just want to have a reasonable core model to get started with for the optimization calculations. And so I will move to the methodology. We use the genetic algorithm as a methodology for the optimization calculations. So to define the optimization problem, we need to subdivide the problem into 3 parts. The first part is to determine the parameters we want to optimize. So here we have several input parameters. So this will form an input space, and we want to determine which core design is the optimal core design. And we also have the objective, so the optimization goal. So here we want to minimize the core power because it's a test reactor, so we want to minimize the core power so to reduce the capital cost of the nuclear power plant. And also we want to minimize the external plutonium mass, so this is the fuel cost. And another one, we want to maximize the PFAS flux because it's for material test purpose. And we also have some kind of constraints, so just to make sure that the reactor core is within the control of the safety system. And finally, we want to have the result, the so-called Pareto flux core results. So the Pareto flux core result you can see here. So this is the input space. So this is the input space, and then we perform the calculation to get the output space. So this point is not the Pareto flux. The Pareto flux is the line shown here. So you can see if we have a result showing at this point here, we can improve both R1 or R2. Say we want to minimize R1 or R2, we can improve the result. But if the result is in this Pareto flow line, we cannot improve it. We improve one parameter without harming another, such as these 2 points. And we also have constraints. So if we have constraints, then if the code design doesn't satisfy this criteria, we just discard those code designs. And before the optimization, we need to discretize the input space just to improve the convergence. So in total, we have 11 billion data points in the input space, and we want to perform optimization to find out the optimal value. So, and the tools we are going to use is mostly the NIMS workbench, and this NIMS workbench is a integration platform. So the ARCO, the Argonne reactor computational code suite, and also Dakota is already coupled within this NIMS workbench. And we are going to use the ARCO suite for the neutronic deterministic calculations, and also Dakota to drive this ARCO suite and perform optimization calculations. So for the calculation flow, the first step is we need to have a reasonable code model to get started with, and then we parameterize this input model to get the input template. And Dakota can randomly sample to generate the input parameters, different set of input parameters samples. And then later we use the ARCO to perform each execution of the input space to get the calculation results. And we extract the output from those calculation results and feed back to Dakota. And Dakota have the optimization algorithm to drive to generate the next generation of input parameters or input code designs. And we go through this loop until we reach the optimal solution or the Pareto flow code designs. So just a little bit about the genetic algorithm. The genetic algorithm is very similar to the Darwin's species theory. So it could complete those individuals and generate, and the best solutions will survive, and then also have the chance to generate the offsprings. And after we generate the Pareto flow, we calculate the normalized weighted distance to determine the best solutions. So a little bit about the calculation result. So it's a video here. So you can see for the first generation, the result is kind of very diverse in the solution space. And then finally after the genetic algorithm, it could search for the optimal space. And then you can see at the later generation, the solution is mostly focused on the optimal space. So this is about how the Pareto flow looks like. And here it shows the result. We have different sets of results selected from the optimal solution, and you can see that compared to a reference result is better. So the further from the control center, the better the solution is. And also a detailed comparison showing here. So if we compare different sets of solutions, such as comparing the W1 and W2, you can see improve in the plutonium external feed, but we sacrifice in other parameters. So there's no free lunch. So in conclusion, the NIMS workbench is demonstrated to be capable of sodium fast reactor optimization calculations, and we also try different methods, and we have more results. But showing here is just part of the result. And the optimization calculation could be computationally very expensive. So if we want to perform a direct physics calculation, we need to have a lot of computational resources. Yep. So thank you.
Thank you. Because you mentioned, in the flow chart model that you have mutation. And
yes.
I would like to understand in the mutation if you are using something regenerative, how you do this mutation.
So the mutation, yeah. So the mutation here. So when we rank the previous generation, and then we extract the input parameters. So the mutation is kind of like assign a ratio, and then have a kind of change in the input parameters, such as maybe the field cladding. field cleaning radius, we change it. We randomly change it. Yeah. So this is just to make sure that we don't have, we don't converge to a worse result. Yeah.
You don't converge to the worst result.
We just to make sure that we have some kind of divergence and then not converge to something not optimal. Yeah.
Okay. All right. Thank you.
Question? Thank you. The next speaker is Yang Mao Zhu, who's a PhD student in Dr. Dennis group. His area of research is machine learning and algorithms.
Okay, so hello everyone. Today I'm going to introduce my topic about development and assessment of a data-driven approach for turbulence modeling. So first I'm going to introduce what is data-driven turbulence modeling and why I'm doing this. So first, thermohydraulic analysis of complex systems such as nuclear power plant, it requires a computationally efficient CFD modeling method. Traditionally, the most common CFD method used in engineering practice is based on solution of RANS, which is Raynold average Navier-Stokes equation. But the model has two limitations, which are calculation accuracy and the complexity of choosing turbulence model and parameters for different flow configurations. And we also have a direct numerical simulation, which is DNS. It is usually considered as the most accurate computational method in the CFD area. It could break the two limitations of RANS, but its computational expense is too large to be used in engineering practice. So the motivation of this study is simple. Since the new simulation result of DNS is available, is it possible to leverage this data to increase the model accuracy of RANS without hurting its efficiency? Furthermore, could the modified RANS model be applied to new configurations whose DNS data haven't been performed before? So this motivation is further inspired by the recent development of machine learning, which provides the technical tools to achieve this goal. We have three main objectives for this research. The first objective is to increase the RANS model accuracy. The second one is to increase the RANS model applicability, make it applicable to a broad range of flow configuration. The third one is to leverage the valuable data from experiment and high-fidelity numerical simulations. Okay, so now after I have introduced why I'm doing this, what I'm doing this for, now I'm going to introduce a technical background of data-driven turbulence modeling. So we have two parts. First part is turbulence modeling. What is turbulence and how I'm modeling it? The second part is machine learning. What is machine learning? What kind of algorithms am I using? So first, the turbulence modeling part. So in order to modeling the tip turbulence, which is a flow dynamic problems, usually we have Navier-Stokes equations. I think most of you have already familiar with Navier-Stokes equations. It gives the description of fluid. But for turbulence problems, you can not only directly solve the Navier-Stokes equation, you need to do time averaged, which will give you the Raynold average Navier-Stokes equations. In Raynold average Navier-Stokes equations, we will have this in the red circle, the Raynold stress part. This part is need to be modeled in order to close the conservation equations. In order to model it, usually we have these turbulence models for RANS. We have eddy viscosity model and we have Raynold stress model. And what are we doing now in this research is trying to develop another one, which is this red word, the data-driven turbulence models. So we are going to establish a surrogate model between the Raynold stress and the quantity of interest and our high-fidelity data. Okay, so after I have introduced the basic theory of turbulence modeling, now I'm going to introduce a short review of the machine learning part. So what is machine learning and how many algorithms are there available? As you can see, all of this box contains the machine learning algorithms available. So basically, machine learning algorithms are usually classified by their applications. So generally, we have three applications. The first one is classification. The second one is regression. The third one is clustering. And the one we want in this research is regression. So we are using neural network to solve these problems. As you can see, in both of these three applications, neural network is able to do the job. Okay, so what is neural net? How does it work? So neural network, just as its name, it is a network of neurons. For the simplest part, a single neuron, it could be seen as a summation of the weight multiplied by the input. So in the left picture, you have seen this is a neuron. The value of its output is a summation of the input and the weights. So what I need to train is to train the weight, which is W1, W2, W3 in this single neuron. So if you combine this together, it could form a neural network, and you have different methods to combine them, which gives you different kind of neural network. This is the picture of neural network family. It tells you how many neural networks are there available, and different type of them have different functions. Okay, so now we have introduced what is turbulence modeling and what is data-driven, and now I'm going to do is to show you a framework that combines them together. So this framework is what I use in my research. So we can separate them into three parts. First part is database preparation. Second part is surrogate model establishment. And third one is to make model validation. So what we do? So usually what we do is we first you have DNS data, which as you can see is the left up corner. We have DNS data, and we also have RAS data. So in our framework, first we will obtain the velocity field from DNS data, and we put the velocity field into the RAS equation to get the RAS level Briganoid stress. And we will also have RAS data, and we will obtain the quantity of interest, which is the Q part in this RAS data. So now we have the training output and training input for the machine learning model. So the second step, we train the surrogate model, which is this FML, which is the machine learning algorithms we use. So after we train the surrogate model, the next, excuse me. Yes, thank you. Okay, so after that we will do the model validation part, which is taking the machine learning model into the practice and to validate our data. Okay, so now we are going to our case study part. So the first case study is for the 1D channel flow problems. So in these cases, we have training data and the testing data, all for the same geometry but different noise number. We use training data of these three practice as training data to predict another cases with same geometry but different noise number. So this is the result. As you can see from the right up picture, we have blue lines, which is the baseline, which is the one that is incorrect, but we use it to. We are going to make a correct correlation. We are going to make a correction based on the baseline. The blue line is the one that is incorrect. The black line is DNS profile, which we consider as the accurate result. And now we are going to do the correlation based on our machine learning model. And after that, we will obtain the red circle line, which is the prediction line. So as you can see, our prediction is agree well with the DNS data. So this is the first exam. So in order to recap, the first exam, we have same geometry. We predict another cases with same geometry but different noise number. So in the second case, we will try to predict another cases with different geometries, which increase the difficulty. In these cases, we have this geometry configurations of 2D channel flow, and we slightly change the geometry by changing the parameters of A meter, which is the step height. So by changing these parameters, we slightly change the geometry. And in this case, we have training data in this blue circle and testing data in this orange circle, as you can see, because we are using a different height ratio. So the testing case have different geometry as the training data. So as you can, so in this result, as you can see, as long as we increasing the data amount of the training data, finally we get our prediction result, which is agree well with the validation result. This x-axis is the validation result, and this y-axis is our prediction result. Okay, thank you for listening to me.
Navier-Stokes equations.
Excuse me.
But it is not really necessary to use Reynolds average. You can use a Reynolds number in a set of equations that can be classified into the Navier-Stokes equation according to the value of the Reynolds number without taking an average.
Excuse me, I'm not quite understanding.
You mentioned that it's traditionally in computational fluid dynamics that they are doing Reynolds average.
Yes.
But it is not necessary.
So
It is not necessary at all. Because you can do the full solution of Navier-Stokes with, a set of equations for the change in the Reynolds number. So you don't need to take an average. This is a comment just for you to know. Number two, you showed the equation, and I wasn't really very much sure if you are using an equation that's, a K epsilon.
yes, I use K epsilon model as a
So
baseline.
it's a K epsilon model.
Yes.
All right, because also you can use a K omega.
Yes,
Wow.
yes. The
Which
model.
can simplify things.
Yes.
Right, okay, thank you so much.
Why don't you use the neural network or other methodologies?
There is a comparison of the advantage and disadvantage of the different algorithms, but because this is a 10-minute presentation, so I didn't put these slides. If you're interested, I can introduce it later. So generally, I use the neural network because the prediction speed is fast, and this is a main advantage of neural network and Gaussian regression process.
Yeah, I ran into the same thing as you, so it took me some time to figure out what's the best. I'd be curious.
Okay, thank you.
So I wanted to say,
So you mentioned the application of
Yes.
so what do you mean to use it?
DNS is selected as a high fidelity data, so we are using the DNS data as a high fidelity data to train the model, so that we want the RANS model to approach the DNS accuracy. You get the idea?
So where do you get the DNS?
So for this case, this is a case performed by Dr. Morse in University of Texas. So the DNS data is available online.
Because I was thinking about our group, and I thought, well, we never did such a case.
Okay, thank you.
okay, I wanted to thank the students twice who spoke. First, for agreeing to speak at such short notice. It was very short notice. Second, for keeping us on time. I said I was going to finish in 50 minutes. 55 was close enough. Thank you, so thank you all for coming. See you next year.
Nothing like you. What about you? Sure you want to watch it? Yeah. Or you want to come over and watch at my place? We could.